Hello, everyone. Thank you once again to be again on one of our events of the ESO Hypatia Colloquium. As always, let me remind you that this is a series of colloquia specifically designed to give the chance to early career astronomer to talk about the scientific results. We are very happy to have, and we congratulate all the time with the speakers who were selected through a very competitive selection process. So today, so we have two talks today that will be introduced by our chairs of today, who are Tommaso Marchetti and Stephen Molineux, who are both a fellow and a student of ESO. We are very happy to work with them, to have them with us, and thank you very much for volunteering to chair the sessions. So very, very quickly, technically, people can make questions either by using internally using the chat on Zoom, by basically raising the question. Even better, you raise your hand and then you can make a question in Zoom, or you can basically, the people following the talk on YouTube, they can make a question, write it down on the chat. If you are not comfortable with that, you can also go to our pages, and there is a form that you can fill to send your question directly via. So basically, you fill the form, you put the question, you press send, and the question is sent to us by email, and then we will pass it to the chair of the session. Just to let me remind you that these videos are going on, as you said, live streamed on YouTube, and they will stay in our Hypatia channel, where there is a playlist where you can see also all past events. And on the other side, you can go to our pages. There is the program pages. You can see, of course, the series, entire series, but you can also click on the title of this talk, and by clicking on the title, you are able to access the PDF, or not only on the information about the talk, but also about the speakers. So you will have access to the curriculum vitae of our speakers, which is a very big source of information about our new generation of astronomers. So please, with this, I will give the voice now to Tommaso to chair the session. I would like to thank everyone for joining us, and enjoy the event again. Thank you.
Thank you, Giacomo. Hello, everyone. Good morning and good afternoon to all of you. My name is Tommaso Marchetti. I'm a fellow at ESO in Garching, and it's my great pleasure today to co-chair together with Stephen today's Hypatia Colloquium. So the first speaker of today is Philippa Hartley. Philippa got her PhD at the Jodrell Bank Center for Astrophysics in the University of Manchester on finding and looking through strong gravitational lensing. And since 2019, she's now a postdoctoral fellow at the Square Kilometre Array Organization. And Philippa works on radio interferometry observation and modeling of strong gravitational lensing, and also on how to use machine learning to model the interferometric data. So the talk of today, the title is Cosmic Telescopes Witnessing the Emission Mechanism of Radio-Quiet Quasars. So Philippa, the stage is yours. You can share the screen.
Thank you so much. Thanks for that lovely introduction. And thank you very much to the organisers for accepting my abstract and for creating this wonderful series. I'm really excited to be here today, a little bit nervous, but really excited to talk to you about how we are using strong gravitational lenses to look at one of the oldest problems in radio astronomy. So I've divided this talk into 3 sections. In the first section, I'll give a bit of a recap on what radio-quiet quasars are and why they're important in our understanding of galaxy evolution. I will then touch on gravitational lensing, again, another recap, just to show you how we can use strong gravitational lenses as cosmic telescopes to look at really faint background sources. And finally, I'll combine the two together to show you how we're using cosmic telescopes to look in detail at radio-quiet quasars. So, radio-quiet quasars. Okay, quasars were discovered over 60 years ago now. Initially, using radio telescopes like the beautiful Lovell telescope at Jodrell Bank in the UK. And that's how they got their name, quasi-stellar radio objects. They were quickly associated with really point-like, star-like objects in the optical. And the optical spectra revealed that these objects were actually extremely highly redshifted compared to sources we'd seen in the past, with the implication that they're extremely far away. So actually, they weren't stars at all. They were objects coming from very distant galaxies. And then with the implication that the power they must have must be extremely high for us to be able to see them. And it turns out that they have this really high power across most of the electromagnetic spectrum. And in some quasars, they have extremely high power in the radio as well, where we see these dramatic jets that terminate in diffuse lobes coming from the core of the quasar. But it also turns out that in most quasars, the radio emission can't really be seen. And in fact, these quasars are radio quiet. And they make up about 9 out of 10 of the quasar population. It's a bit mysterious. You don't really see jets and lobes in most quasars. And we're still not quite sure why, but we're also not sure. We can see some radio emission, and we're not sure exactly where that originates from. It could be that the radio emission we do see in radio quiet quasars comes from scaled down versions of their radio loud counterparts. So we know that radio loud emission in the huge jets and lobes originates when the really violent processes that are tearing up accreted gas and dust near a central supermassive black hole are resulting in the collimation of matter. So all this plasma is ejected, essentially ejected from the heart of a galaxy and travels at relativistic speeds away from the core. Maybe in radio quiet quasars we have that going on, but on a smaller scale. Alternatively, maybe what we're seeing in the radio is star formation activity in the host galaxy. So we know that in some galaxies, particularly starburst galaxies, you can see really high-powered radio emission going on as the result of supernovas turning over very fast star formation. There is a limit to this emission, and we can use the brightness temperature to quantify that. So in these regions, we can see a maximum brightness temperature of about 10 to the 5 Kelvin, which we can use a bit later on. And the bigger picture here, in terms of quasars, is what is the role of radio quiet quasars in galaxy evolution? So we know that galaxies evolve from being blue and star forming to being red and dead elliptical, where star formation is no longer happening. This seems to happen on very fast scales. And we know that the quasar population seem to peak over cosmic time with star formation activity. So it looks like the two are related. But we don't know exactly how star formation becomes quenched. In the radio loud quasars, we can see that jets might heat up the host galaxy gas, preventing it from cooling and preventing stars from forming. But in the radio loud quasars, we also suspect some kind of so-called AGN feedback might be going on. This possibly in the form of winds blasting through the galaxy as the result of AGN, the very, very bright radiation coming from the AGN, or possibly even, again, some kind of jet activity. So it's really important to be able to see what's going on if we're going to understand the full picture of galaxy evolution. And there's an awful lot of evidence in the literature going back decades that makes this a really hotly debated topic. There's evidence for the fact that these radio quiet quasars may be a population that contain a lot of star formation. And that comes from things like looking at the quasar luminosity function, where as you get to fainter and fainter luminosities, you start to get a bump in the luminosity function, which can be really well modelled by a star forming population. On the other hand, there's also evidence that the radio quiet quasar population, that the radio emission from it is produced by AGN origins like jet activity. For instance, some authors have used the radio far infrared correlation that's very tightly stuck to in star forming galaxies, really, really tight correlation between radio and infrared emission. And if you take a sample of radio quiet quasars and compare that with the correlation, you tend to find you get a radio excess. So it can't be explained by star formation alone. And it implies that there must be some kind of additional mechanisms like AGN jet activity going on. Right, so as I said, it's hotly debated, has been for decades and still is really. So what we want to do is use another phenomenon, another astrophysical phenomenon known as gravitational lensing to allow us to get a closer look at these objects on a case-by-case basis and see exactly what's going on in them. So a really quick primer on gravitational lensing. We tend to think of three regimes when we talk about gravitational lensing. There is weak lensing, which is typically used to map out really cosmic scale dark matter structure. So we can see the filaments of dark matter and use that to, say, study cosmology. We can also use gravitational lensing in the micro regime, where we're looking at really compact objects that change the brightness of sources behind them, which allows us to discover things like rogue planets. But today, we're interested in strong gravitational lensing, and this is when you get two typically galaxies aligning very tightly along your line of sight. When this happens, the mass of the intervening galaxy is able to magnify the background galaxy really strongly, and stretch it across, stretch it so that instruments that are looking at it effectively have a much higher resolution. So I'll just talk you through a really quick schematic of what's happening in these cases. On the left-hand side, you have a source and how it would look without a strong gravitational lens in the way. On the right hand, you have what the source looks like when a lens is intervening. Also important to note are these lines of magnification. These are really important, and it's the position of your source with respect to these magnification lines that tells you what you might see in the lensing plane. So if we take our source, the black dot on the left, and we bring it towards our line of sight with the galaxy, we see first where it is at the moment, it's been split into two in our lensing plane. If we move it in closer to our line of sight, it gets magnified and magnified until it hits the line of so-called infinite magnification. At this point, it's highly, highly magnified and highly stretched. So we get the maximum amount of benefit we can with a strong lens. Move it in closer, and you end up with an Einstein cross. And you typically get between factors of about 10 to even 100 magnification on the brightness of your background source. So you can use strong lensing to see sources that will only be observed in the future, or would only be observed by future telescopes like the SKA, really sensitive instruments. Okay, so combining the two, using strong lenses as cosmic telescopes is what I want to talk to you about. So this is a programme that was begun by my PhD supervisor, Neil Jackson in Manchester. And the idea is to look at all the quadruply lensed radio quiet quasars. So quadruply obviously just means they've been lensed into 4 images. And I want to talk to you about results from 3 sources in that population today. So it's these sources are obviously quite rare. Strong lenses themselves only occur about 1 in every 1,000 sources. And quadruply lenses are even more rare, but they're extremely useful. One of the things you'll notice is that you get in these quad lenses that we've got here, you've got these 2 so-called merging images. These are also really useful for studying the distribution of structure in your intervening lens. And that's because the magnification at these images is highly sensitive to the structures in between us and the background source. And it's also highly sensitive to the size scales of dark matter. So you can use that as a window on cold dark matter substructure, but that's outside the scope of this talk today. Okay, so if we take a look at our first source in the trio, what we wanted to do, the idea is to use the really high resolution of radio telescopes like the European VLBI network, which is a network of huge telescopes connected all over the world. When you have telescopes really far apart, you increase the you increase the resolution of your radio interferometer. So you can see a really high resolution. And that means the telescope is really sensitive to very compact source sizes. And the special thing about interferometry is it becomes insensitive to large scales of structure. So if you can see something with the VLBI, you know it must be really compact. So this makes a really nice test to see whether we can see jets in radio quiet quasars. And indeed, we did this test with this source, and we found that we do detect it with the European VLBI network. And the combination of the resolution of the instrument with the magnification of lensing as well gives us a really high constraint on how compact it must be, and allows us to say it has a really high brightness temperature, about 10 to the 8 Kelvin. So if you compare that with our starburst facts, we know that it's too high to be produced by starburst activity. It must be AGM related. We can also do modeling. So we can take a model of our lensing system, model the lens and the source, and it allows you to project your emission back to the source plane. And when we did that, we modeled the radio emission as well, alongside the optical emission from HST. And we found that there are two really compact sources that are aligned in a linear configuration with the optical core. So really reminiscent of a jet morphology. And we say that this is strong evidence for sub-parsec jets in this source. They're also sub-microdensity, which is so far the faintest radio sources observed, intrinsically faintest anyway. We've got the power of lensing to see them. And it turns out that most of the radio emission in this source can be attributed to these jets. So minimal star formation is happening in this source. So maybe star formation is quenched in this object. And intriguingly, in the literature, other authors have found that this source contains ultra-fast outflows of gas. So going not quite relativistic, but very high speeds, up to 0.4 times the speed of light, which, yeah, is quite intriguing. Also intriguing is the position of this source on the radio far infrared correlation. So we know that in so-called jetted sources, you should expect to see an excess of radio emission above the radio far infrared correlation, this diagram of the correlation is flipped with respect to the previous one. However, our source with the twin jets appears to lie below the correlation. So we very tentatively suggest that, well, question whether the correlation can reliably be used to rule out jet activity. And we take another look at the correlation in our second member of our trio of sources. So here it is. It's another quad-lensed radio quiet quasar. We have radio observations using VLA, where we can see that the emission in the radio, the lensed emission at least, is quite extended. It's not as compact as in the optical, which really suggests that there's some kind of really more extended emission in the background going on. This analysis is in preparation and hopefully being submitted soon to monthly notices. And one of the things we are suggesting is that if you use the emission values in the far infrared to model the spectral energy distribution, you can see that the model suggests that there are two components that contribute to the far infrared emission, two dust components. A warm one with an effective temperature of over 100 and a cool one of about 30 Kelvin. If you then take that cool dust component and use it to recalculate where your source is on the correlation, you find that it actually moves across to have a radio excess. So perhaps, again, very tentatively, we suggest that there are other processes that can conspire in some radio quiet quasars, at least, to put them on the correlation that are not just to do with star forming activity, possibly related to the AGN activity itself. And as I say, these results are in preparation, so look out for them soon. And also, intriguingly, again, this source has been observed to have the ultra-fast outflows like the previous source. So very tentatively could have a scenario where there are mini jets that are responsible for coupling with gas in the host galaxy and blasting it away and preventing star formation from happening. Finally, very quickly, this is the final object in our trio. Again, we have tentative evidence for jet activity, which is seen through the variability of the source. And you can read more about that soon, hopefully. But I just wanted to point out before I finish that there is other evidence. Some of my collaborators and also other authors have looked at other strongly lensed radio quiet quad quasars and found really strong evidence for star formation activity. So on the left, you've got this velocity dispersion map on the bottom, where you can really see evidence for a lot of turbulent star formation going on. And the authors attribute all the radio emission in that source to star formation. On the right, one of my collaborators has imaged this source, this other quad lens, in the radio and in CO line in the far infrared, and found that the emission seems to be coming from the same place at both frequencies. So it seems to suggest that radio emission is coming from the rotating molecular disk, and therefore implicating star formation activity in this one. So the picture is really mixed, and it just makes the problem more interesting, possibly. And some authors suggest that the radio emission mechanism and whether there can be jet activity or star formation ongoing in radio quiet quasars is not necessarily down to the AGN, but perhaps down to the morphology of the host galaxy, which brings me to my conclusions. So radio-quiet quasars, they're not fully understood, but their role in the suppression of star formation is likely to be very important. We can use strong gravitational lensing to look at these things directly, which means we avoid having to use, we avoid sample effects and bias. It's a mixed picture, so we've seen strong evidence in some sources for jets and in some for star formation, and that's probably why the arguments have been able to persist for so long in the literature. We have a question of maybe it's a bit of a chicken and egg situation. So we're assuming that feedback from the AGN affects the galaxy, but maybe the galaxy also affects what can happen in the AGN. And we're continuing our programme with new exciting observations. So please stay tuned to hear news about those in the literature. Thank you very much.
Thank you very much, Philippa, for the really great talk. It was very clear. Thank you. So are there questions for Philippa? I just want to remind you, everyone, that you can either questions here in the chat Zoom, you can raise your hand here in Zoom, or ask in the YouTube channel, or also send it through the form, which is available on the ESO Hypatia Colloquium page. So there is a question from Giacomo. You can ask your questions.
Yeah, Philippa, sorry. Thank you very much. Very much, and congratulations for the work. I'm sorry because this is not my. That's a nice thank you. Actually, now I noticed the face. That's funny. Thanks. I wanted to ask you. I'm sorry because it's not my field, so I hope this question is not too. I mean, bad. but in your second example, second case, you show the VLA email map. Let's put it map. And I was wondering, so you mentioned that this A1, A2 is an extended emission, right? I was wondering how, which is the impact of the, I guess you call beam size in this range, or say the resolution. So how can you be sure that there is not a resolution issue here?
Oh, that's a great question. Yeah, I think if we just look at the map in itself, we can see there's this sort of excess arcing going on. So if it was just a resolution issue, we would still see like merging blobs, but we wouldn't have this kind of characteristic, if you can see the arcs extending a little bit to the south. But what we have done as well, and what I didn't have time to mention today, we also are modelling it. So we have some preliminary models that also show the background source is quite extended. I
see. Okay, so it is supported by modeling, basically.
Yes, it is. Okay. Yeah.
And another question, if I have time to follow up question, maybe Tommaso. Okay.
Yeah, sure, of course. Go ahead.
I was wondering how. So again, this lensing science is really fascinating. Has always been fascinated by this. But how do you define your targets? So how and your feasibility of your observation, in a sense, or your program, in a sense? How many targets you can explore? How you decide them? So how do you find them? All of this.
Yeah. I'd love to talk to you all day about this. I mean, so for us, we've defined it quite tightly by looking only at the quadruply lensed quasars that are available. And until recently, that's been just a handful of sources. So we've really been able to spend, it's been reasonable to spend quite a long telescope time looking at each one because there's just a small amount of them. Obviously, that will increase really soon when we have things like Euclid. So hopefully Euclid will be taking off in the next year. And I am involved in some lens finding activity as well, which complements the work of actually studying them. So part of my PhD. So the thesis title was Finding and Looking Through Strong Gravitational Lenses. So yeah, so finding them, in things like the Euclid surveys, Euclid will see billions of objects, billions of galaxies, and among that there will be tens of millions of millions of strong lenses. So it is about finding them, because there are going to be some super useful systems. So the work is ongoing to do that. It's really important work. But at the moment, we're basically looking through current observations in the optical and determining if they are suitable for follow-up in the radio.
Okay, I see. Great. Thank you very much again.
Thank you.
So are there more questions for Philippa? Okay, in the meantime, I will ask one. Again, also, this is not my field as well. So, but you showed that for this quadruple image AGN, basically for merging images, you just mentioned that they can be important for testing the cold dark matter substructures. So yeah, I was interested in that, if you could say a bit more about that.
Okay, awesome. Yeah. So yeah, there's just so much you can do with strong lenses, and so cosmic telescopes is one brilliant use, but the other use is, of course, studying the actual lens in galaxy. So you can, because the distribution of the light is essentially mapping out the distribution of all the matter in the galaxy, you can look at the macro distribution of your galaxy. So you can use it to constrain profiles of galaxies, but on the very small scales, you can use it to study cold dark matter substructure. So we know that cold dark matter paradigm predicts that substructures of dark matter can go smaller and smaller. So you should be able to see in galaxies, either dwarf galaxies around normal galaxies, or perhaps we don't see dwarf galaxies because there are lumps of dark matter, but they're not populated by stars. So you can use strong lensing to try and find those dark lumps of dark matter. And when you have a quad image like the ones with the merging images, those you can use your lens model. So because the lensing model is so deterministic from Einstein's general relativity, it's kind of quite simple, really. So if you get a deviation from the prediction of, say, the magnification at these images, you know that there's probably some extra stuff there, and it's as simple as that. So we can use it to try and see if we can detect dark matter on these very small scales, or perhaps we can't see it. And if we can't see it on those tiny scales, then maybe there's something wrong with cold dark matter, which is really exciting.
Thank you for the very great explanation. It's really, really interesting.
Cool.
So let's see if there are more questions. Otherwise, yes, the talk will be online, so people can ask questions there. So, okay, if not, let's thank Philippa again. Great for the really beautiful talk. Thank you so much. So, and now we can go on with the second talk of today. So I will just give the word to Stephen, who will chair the second session. Thank you so much.
Thank you so much. Thank you.
Thank you very much, Tommaso, and thank you, Philippa, for the very nice talk as well. So hello, I'm Stephen. I'm a second-year PhD student here at ESO, and it's my pleasure to welcome our second speaker of today, which is Joaquín García de la Cruz. Joaquín is working on galactic archaeology using thick discs in galaxies, and I'm really excited for his talk today, which is titled On the Flaring of Thick Discs, Insights from Simulations. So Joaquín, whenever you're ready, you can share your screen, and the floor is yours.
Thank you, Stephen. Okay, let's go. Thank you very much for nice introduction. And thank you everyone for being here. So as Stephen said, my name is Joaquín, and I'm a last year PhD student. And today I'm presenting a summary of the results that I got published a few months ago, and that were done in collaboration with Mari Martik, Ivan Minchev, and Phil James, where we use simulated galaxies to study the thick disks. So I'm going to start with an introduction. So what are thick disks? People, when they observe external galaxies, and they look at the vertical light profile in the disk area, and they usually decompose these light profile into two components. So one that is less extended, which is the thin disk, and the one more extended, which is the thick disk. And usually in this decomposition, people, for fitting the data, they use exponential-like functions. And for these exponential-like functions, there is one parameter, which is the scale height, that is very important. And it's basically telling you how extended in the vertical direction your component is. In the Milky Way, of course, we cannot see the disk of the Milky Way from outside, but we have access to a lot of information as well. And so people have defined the thin and the thick disk based on different properties. For example, kinematics, chemistry, age, stellar density. But today, for this talk, when I speak about the thin and the thick disk, I'm going to be referring to the geometrical thick disk. So the one defined by the stellar density, because it's also equivalent to the observations of external galaxies. So what do we know about thick disks? Large surveys of large samples of galaxies, they concluded that thick disks were flat, so the scale height wouldn't change with radius. But this was challenged by recent observations where people have seen that the scale height can increase with radius, and this is what we call flaring. In the Milky Way, we know that the inner disk is flat, so the scale height doesn't vary. But then in the outer disk, whether it does or not, and how much it does, is still a matter of debate. The H structure in the classical view of thick disk was that the thick disks were basically red all metal poor components, and also quite homogeneous. But this view is also being challenging by recent observations. So for example, if you look at the green dots over here, you see that these thick disks are like 5 or 7 gigayears old, whereas this one is older than 10 gigayears old. So the age can be very different, but also there is a lot of substructure, right? And they are not homogeneous at all, as you can see in this plot. In the Milky Way, we know there is H substructure for sure. And for example, the existence of radial H gradients have been found. And this is because in the thick disk, different populations live in different parts of the disk. Whether the thin and the thick disk relationship is meaningful or not. So when we decompose the disk into the thin and the thick components based on the stellar density, can tell us something about the disk. Well, in the Milky Way, people have studied this. So for example, this is a plot from Macrath et al. In 2017. And they're plotting the stellar density as a function of the scale height for different mono-age populations, right? And if you look at the green dashed line, what you see is that this stellar density decreases smoothly. And so there is no clear point where the thin disk ends and the thick disk starts, but it's all part of the same continuum. But maybe in other galaxies is different. And indeed, we have observed these in simulations. So this is an adaptation from a plot in Martig et al. 2014. And here there is the scale height as a function of radius for different mono-age populations, color-coded. And what you see is that the scale height increases with age, right? And increases smoothly for this galaxy. And again, the density also decreases smoothly. So basically the thin and the thick disk, they all seem to form one continuous structure. But then there are other galaxies where the scale height shows gaps, and these gaps, we know they are caused by mergers, and I'll come back to this in a few slides. And so when you have this kind of configuration, then the stellar density of the disk is clearly divided into two groups of stellar populations, right? So could this be defining the thick disk and the thin disk and this the thick disk, and therefore this decomposition be meaningful? Let's not talk about how thick disks form, because many information processes have been proposed, and I'm listing some of them here. But I would like to direct your attention to a conundrum that there was a few years ago, because Lambda CDM would predict that galaxies would undergo mergers, and these mergers, they would make the thick disk flare. But then we observed a lot of galaxies with flat thick disks, right? They were not flaring. So what was going on? So Minchev et al. In 2015 proposed a mechanism by which you could have different mono-age populations flaring, but still recover a flat thick disk, right? As you see in this picture. Because this is a very important point for the talk. I'm gonna spend a few minutes to talk about this effect. So here you have a simulated galaxy from the sample I work with, and this is a density map seen face on and edge on. And I'm plotting here the scalar height versus radius for the thin disk and the thick disk, right? And you can say that with some fluctuations, the thick disk is, more or less flat. But then if we bin the stellar populations by age, things look very differently. So if, for example, we center on the very old populations, we see that these populations live very in the center of the galaxy, right? And they flare a lot, but the density is not very significant in large radii, right, in the disk. If you go to slightly younger ages, these populations are more extended in the disk. So, their surface density is more significant at larger radii, but also they flare less, especially in the inner part. And if we go to younger and younger stellar populations, this effect goes on. So basically what is happening is the old populations may flare, especially at large radii, but because these populations don't dominate the stellar density and this part of the disk, but actually younger populations, which are flatter, dominate the stellar density in this part of the disk, the flaring doesn't count, and so the global scale height of the thick disk is going to remain flat. Okay, so the goals of the project was to analyze a whole sample of galaxies and analyze how the flaring of different mono-age populations look like, and how that is related to the global shape of the thick disk, whether they flare or not, what kind of disk they would create, a continuous structure or a bimodality, what kind of age gradients they would create, and finally, because the flaring configurations of the mono-age populations is connected to the merger history of galaxies, how this all also could be connected to the merger history of galaxies. So the sample I use is published in Martic et al. 2012, and the sample consists on 27 Milky Way-like star-forming spiral galaxies. And these galaxies present a diversity of asymmetric features, bulk fractions, and they all have different major histories. Right? This is an example of 5 density maps and age maps for 5 galaxies, and you can see how actually there is a lot of diversity. So we found 2 cases where flat thick disks can be created. The first one is when basically all the mono-age populations don't flare or flare very little, right? Then how much surface density, which I'm plotting here as a function of radius, where they dominate each mono-age population, well, it almost doesn't matter really much because none of them flare actually. So they're not going to drive thick disk flaring. The other example is where you have some mono-age populations flaring quite a lot, but then when you look at their surface density is very little, right, compared to other younger and less flare stellar populations. So this is actually a very similar example to what I showed previously. Then for flat thick disks, we found also two main scenarios. One is when the older populations, which are flaring, carry enough surface density to make the thick disk flare, right? And you can see here how the surface density of the older populations more or less has the same proportion all the way through the disk. And so these stellar populations have enough surface density to make the thick disk flare. The second case is when a group of stellar populations, they share the same scale heights, right? So this group together, they have enough surface density to make the thick disk flare and actually follow the same scale heights that they have, right? And so this is the main four scenarios that we find. Now, how is this connected to the bimodality, or like the distinction between thin and thick disks? So I made plots similar like this, and this is what we find. For galaxies like this, you can see how the scale height increases with age, right? And also the surface density decreases with the scale height very smoothly. So in this case, the thin and the thick disk are forming, a continuous structure. And this is the same case for the basically all the flat thick disks. But then a case like this is completely different, because as I said in the introduction, you have two groups of galaxies very well distinct, and in this case, this group of galaxies is making the thin disk, and this group of galaxies is making the thick disk, right? So in this case, the composition based on stellar density is meaningful and is clearly showing two different components in the disk. Then we also find an intermediate case, because you have some gaps in the scale heights, but the stellar density doesn't decrease smoothly. You have some peaks, but it's not as strong as this. So we call this a mild bimodality, right? An intermediate case. So let's go on to age gradients. What kind of age gradients we would expect in a case like this? Well, because of the inside-out formation of the galaxy, old populations, they dominate the stellar density in the inner part of the disk, and younger populations, they dominate the stellar density in the outer part of the disk. So if we plot age as a function of radius for different heights above the midplane, what we see is a decreasing age gradient, right? Which is what we expected. And the black dashed line here represents the age gradient following the scale heights of the thick disk. And so it's a decreasing gradient. For this case, is very similar to the previous one. So we also find decreasing age gradients. But then in a case for flat thick disks, because these mono-age populations still have enough surface density at large radii, they are gonna flatten the age gradients. Right, and this is exactly what we find. I think you can see in the age gradient of the scale heights of the thick disk that is way flatter. In a case like this, it could also be flat, but you still have some the older populations in this part of the disk still dominate over these ones, right? So you still have a decreasing age gradient, but you have also this very distinct feature, because you are basically going from the one component of the disk, which is clearly older, to the other one, which is younger. So if we put everything that I've just said together, then what we find, what I'm plotting here is the thick disk gradient. So basically flat thick disk would be here and flat thick disk would be here. And then here I'm plotting the H gradient, right? So we would have strong H gradients here and flat H gradients up here. And if I put all the galaxies of the sample in this plot, then this is how they look. So there is a little bit of a scatter, but we find that galaxies with flat thick disks, they all have H gradients because you can see this part of the plot is not populated. And on the other hand, galaxies with flat thick disk, although there is scatter, they seem to like to populate this part of the plot, right? Then we can also apply the classification that I mentioned before, whether they are a continuous structure or there is a bimodality in the disk. And that what we find is that these flat disks, they tend to be no bimodal, they tend to be continuum. And then flat thick disks, they also tend to show more bimodality, as you can see. Okay, so then we can go a step further and ask how all these relates to measure histories. So what I did was I color coded these points by the measure ratio, the mass ratio of the most massive merger in the last 9 gigayears. Right. And what you can see is that galaxies with flat thick disks, they tend to have more quiescent merger histories. Right? And on the other hand, in galaxies with flat thick disks, they tend to have busier merger histories with large mass ratios. So there is one galaxy that I would like to point out, this one, because this galaxy is 106. It has been used in other works because it's an analog to the Milky Way. And so basically, to recap, what we're seeing is that galaxies with flat thick disks, right, they tend to show no bimodal structure. So the thin and the thick disk forms a continuum. Then they all seem to have H gradients or strong H gradients. And then they tend to have quiescent measure histories. On the other hand, galaxies with flat thick disks, they are more diverse, but they tend to have bimodal structures. So the thin and the thick disk, in terms of density, are clearly defined, and they're made of 2 different populations of stars. And then they also have smaller H gradients, right? So, and they have richer measure history. So all these features, they seem to be in common with what we know of the Milky Way so far, whereas all these features seem to be in agreement with these more diverse picture of thick disks that it seems that is emerging. So I'm gonna leave the talk here. Thank you very much. And I will go back to the conclusions so that you can ask questions now. Thank you.
Thank you very much, Joaquin, for that very interesting talk. So do we have any questions? Just a reminder again, you can raise your hand in Zoom or also type them in the chat in Zoom. You can type your questions into the chat on YouTube, and there's also the online form as well. So I see we have a question from Giacomo, if you'd like to unmute.
Indeed, Joaquin, thank you very much. Very interesting. Again, not my field, but it was very clear. And I wanted to ask you, I have 2 questions actually. If you go back to the thickness versus age plot, basically, and I was wondering, so if I understand, this is a snapshot basically of the observations of galaxies that you have at your disposal, but is it also an evolutionary sequence in a sense? So are galaxy expecting to move one way to the other? So I don't know, from zero thickness to I mean, age. So you see what I mean. So they
it's interesting. This is the first time I think about this actually, but I guess it would make sense, because if a galaxy has a merger happening now, right, then I would guess the age gradient would flat, right, and probably the thick disk would flare. So perhaps it would go from this part of the plot maybe more upwards.
Mm-hmm.
I mean, I didn't have time to show the other plot, but there is also a trend with stellar mass. So these galaxies, they tend to be less massive. These galaxies tend to be more massive. Of course, it makes sense if these galaxies have more mergers or more massive. They tend to be more massive. But yeah, it could be that maybe galaxies go from this part upwards. But this is the first time I think about it actually. So yeah, it's interesting.
Okay, thanks. And I have a second question, maybe. So concerning the bimodality, how does a galaxy ends in a certain being? So it is in the sense, is there an environmental dependency? So I don't know, galaxy in clusters tends to evolve a certain way with respect to, I don't know, others. So
yeah, so all the galaxies from these sample of simulations, right? They all grow in more or less isolated environments. So I don't know exactly how the picture would be in galaxy clusters. I guess there are also other factors, like, for example, ramp pressure and things like this that come into play. And yeah, I guess the picture is even more complicated then. But
indeed. Great. Thank you very much again.
Thanks to your questions. Yeah.
Thank you very much. Do we have any other questions? I don't see any others at the moment, so maybe I can ask another question. So in the plot you're showing here, there is one galaxy at the very bottom, number 59, which seems a bit of an outlier. I was wondering if you could, I don't know, say anything about that particular galaxy.
Yes. So I guess for me, one of the main takeaway messages is that galaxies are very diverse. And so it was really hard in this project to go from studying case by case, all the galaxies to get some general trends. So yes, definitely this galaxy seems to be an outlier. This galaxy in particular developed recently a stellar ring in the outer parts of the disk, and this ring is a little bit tilted as well. And so these could be making the thick disk flare, especially in the outer parts, but at the same time keeping the age gradient, right? Because this outer stellar ring is very young. So yeah, basically when you go case by case, each galaxy is unique, and of course you have a diversity and outliers. But yeah, for the particular case of 59, this is what's going on.
Okay. Very nice, thank you. I don't see that we have any other questions, so maybe I can ask another quick one. So on this, the bimodality and like the continuous in the sample. So my question is basically how common are the bimodal, the bimodal ones and the continuous ones within your sample?
Actually, I think I don't remember the number by heart, but they are kind of even. Yes.
Okay, so there's not one that's sort of more common than the other. They're just,
In our sample, it doesn't seem that way.
Okay.
Yeah.
Okay. We have still no questions from anyone else, but of course, Joaquín is available. His information is on the website if you want to contact him for any other questions. But seeing as we have none at the moment, I'd like to thank Joaquín again for a very nice talk. And I will pass back to Giacomo to finish the session.
Yeah, indeed. Let me also thank you, Stephen. Thank you, Tommaso, for chairing the session. And let me thank again Joaquín and Philippa for excellent talks and very exciting science. Congratulations and good luck for the next month and years for your career. Of course, we're looking forward to see you maybe live some point. I hope to meet you all actually very much. But in the meantime, I also hope to see you at ESO. I mean, we are very, I can say that this, and of course we have a fellowship program. So, in October, there will be the deadline. We will make a call for a fellowship at ESO. So both García and Chile. So you're all very welcome to apply, of course. And also we have the studentship program. So you can also apply for that to spend part of your PhD at ESO with us. So we are always looking forward to welcome you at our institute. So with this, I would like to close and see you. Thank you very much for the people attending the talks, and see you all next week. Thank you again.